Alright guys, so are we all back? Almost. We have one more algebraic method to talk about. And then the last thing I want to do today is section 4.4, which is the word problem section of this chapter. Yes. You knew it was coming. Now we'll talk about, so we have the graphical method, we have the two algebraic methods, we have the substitution method, and now we'll talk about elimination method. What's up?
Eliminated.
Oh yeah. Excellent. Eliminate them. So the whole idea behind the elimination method is exactly what it sounds like. I want to directly kill a variable. So the substitution method is very subversive. It's very subtle. It just replaces it with it. I always see this guy in the shadows coming in there. Elimination is just the guy that just comes down and says, die, you know. So I want to directly, so some of you guys appreciate it. I want to directly kill one of my variables. And the process is really crazy straightforward as long as things line up the way they're supposed to. So what do I mean by that? If I have x plus y equals 7, and I have x minus y equals 5, let me see if I can get you guys to go with me. Some people accept this too easily, but part of you should rebel against the idea that I am completely allowed to add those two equations together. So based on what I prefaced saying that with, are any of you like, why the hell should you be allowed to do that? I know you're the math teacher, but what the hell, man? You have to add the same thing to both sides, don't you? So if I add 7 to 5, I get 12. So I added 7 to this side, did I not? I added 7 to that side. So I better add 7 to this side too, right? That's the only way to make it fair. But what is 7? 7 is x plus y. So if I add the equations directly, I am still adding the same thing to both sides. Because it's given that this is that. But I'm just going to add them so that my like terms go together. Aren't they? The really cool thing about the way this is given to me, or actually the way I set this up, is that when I add these, what happens? Yeah, x plus x, 2x, my y's cancel. That kicks so much ass. Right? What's x? 6. So maybe some of you guys can see why I like this method. The only drawback, it's not really a drawback, is I don't have another equation that's already solved for y, but who cares? Yeah.
In the very beginning, when you were saying you're adding 7 to both sides, you were adding the same equation to both sides.
So if I have x minus, watch this, if I have x minus y equals 5 sitting there, if I add 7 to this side, I have to also add 7 to this side. But what is 7? 7 is this. So if I add x plus y to that side, I am following the rule of equations, which says whatever you do to one side, you have to do to the other side. 7 is this. So if I add 7 to this side and I add this to this side, I've added 7 to both sides. Because that is 7. That's why I'm allowed to add equations directly.
It's because their signs are different.
Well, that's Well, that's the good part about it. I'm allowed to add whatever equations I want to together. But the really nice thing about this situation is these two variables, of course, cancel. Right? These y's cancel.
Why do the y's cancel?
Because y minus y is 0. X plus x is 2x. Y plus negative y is gone. 7 plus 5 is 12. And that just is so beautiful to me. Just kill the thing you don't like. I don't like two variables. Die, whatever. Right?
Beta plus
Yeah.
x.
So then if they were both say it was x plus y and that equals 7 and then x plus y equals 5, do you have to?
All right, we're getting there. I just want to make sure everybody's cool with what we got so far. Yeah, Shannon.
Is it always going to tell you to either do substitution or elimination? Or can
Not
you
always.
choose
Sometimes you can choose. So, I mean, this is one that either way would work fine with, right? I could certainly solve, every single one of these has a 1 coefficient, really, so I could solve for any of them that I wanted to.
So that exact same problem, we can do it if we substituted as well?
Definitely. Unless my instructions said, use elimination on the following. Which it obviously will in this section, because the whole point of this section is, this section 4.3, is elimination. All right, now let me build up to a point where I'll show you a problem that you would never, ever want to use substitution on, and elimination makes it easy.
Okay.
And maybe I'll
That I understand.
convert you. So, all right, is everybody cool with the fact that I can add that this is legal? I never want you just to blindly accept it. And it seems like, oh, please be true, because that looks really good. Just add freaking equations. And it's completely legal. Because I am adding the same thing to both sides when I do that. Now, of course, am I done yet? So now you just plug it back in, either one. So plug a 6 in for x. So I get y equals 1. So my answer is 6, 1. Cool. As always, it would be the place where these two would meet if I graph them, right? And that idea never changes. Bless you. So a natural next question would be, what if these things don't eliminate directly? Because you know that's what's going to happen. So what if I had 2x minus y equals, oh, I'm going to make them work. 3 negative x plus 3y. Oh, I forgot what I did. Okay. Yeah. What? How am I making this problem, by the way? If I just made up one without thinking at all, I'll bet you the answer would be fractions. I'll bet you anything. Bet you a lot of money. But what I do is I come up with an answer, and I double it and subtract the other guy, and then I see what I get. So if I pick the point 5, 2, twice 5 minus 2 is 8, I would have put an 8 there. So I pick the answer first. I start with the answer, and then I just do what it says to do to it and write the answer. So I know what the answer is going to be, because I started there. That's good for you, Jeff. Now, if I add these together, which I'm completely allowed to do, why is that not really good? Why is that not good enough? What does not happen that I really want to have happen? Yeah, none of the variables go away. I'm still with 2 freaking variables, right? So I can certainly take any equation I want to and multiply both sides by something, as long as it's not 0, right? So what would really be nice to have right here? Negative 2, right? Because then it would go with that. So I just take the second dude and I multiply by 2. So I just give it what's missing. I can't just multiply this one piece. I got to multiply the whole equation by 2. So keep it true. You guys with me? So we've never had a reason in the past to just multiply a whole equation by something. We normally are trying to divide and get the x by itself. But now we have a reason. We have a 2x here. If only there was a freaking 2 there. A negative 2x. Wouldn't they cancel then? That's the whole purpose. That's why this was beautiful. It was given to me. These are already opposite signs. Positive 1, negative 1. Cancels right off the bat. They gave this to me not in a great way. Screw them. Oh, it was me. So if I double, what do I get if I double the second equation? What do I get? Negative 2x plus 6y equals 2. Now why is it nice? Let me rewrite the first equation. You guys see why that was a good move? Because now the x's actually cancel. So you never add 2 equations together unless something's actually going to cancel. There's no real immediate reason for that.
So just because you're giving the x a 2. So just because you're putting a 2.
Yep.
Is it going to be 2 for every single one?
Hell no.
No.
All right. So, let me back up. Let me back up. Let me back up. Before we keep going there. If I have y plus x equals 4, isn't that the same thing as 2y plus 2x equals 8? Because I just doubled both sides, right? Which is the same thing as negative 3y minus 3x equals negative 12. Because I multiply everything by negative 3. All of those are, is that cool? Is that the same thing? Don't think to yourself, why would I do that? Is that okay to do? Is that allowed? I'm allowed to run around in a circle and go, whoa, whoa, whoa. I don't know why I would need to do that, but I'm allowed to. So right now we have something that we're allowed to do. Now, how do we normally use this property? We normally use this property when we actually use it in the other direction. We add the 4 over, and then we divide both sides by 2, right? We normally divide, because we normally are trying to undo stuff that's being done. You with me? Or if I have a situation where it's 1/3 x equals 4, I would multiply both sides by 3. We know we're allowed to multiply or divide both sides of an equation by anything except 0. I can't make it 0 equals 0, sorry. Is that cool? We know that's true. The reason we've used that in the past is to try to get x by itself, to solve an equation. That's why we've used that rule, that allowance. That's how we've used it. Well, now we have a whole different reason to use it in a different way. If only there's a freaking minus 2 there, these x's would cancel. Thank God I'm allowed to multiply this equation by whatever the hell I want to, except 0. So I'm going to multiply it by 2 throughout. Then that's going to give me a negative 2x there. Now think about it. What if I wanted to kill the y instead? What would I have done? Multiply this first equation by 3. Because then there would have been a negative 3y end up there. Right? Okay, maybe. Yeah, Jerry.
Are you done with that?
No. Yeah. I haven't gotten the answer yet, so I can't be done yet.
So you get 5y for 5, right?
Hold on. Yeah, so what do you get when you add these together? Those go away? 5y plus 5. So y is 1.
Wait a sec, why did you just put that underneath that?
When I add these two equations together, which is the whole reason I wanted a 2 there. So again, the idea of elimination method is to make one of the variables cancel. The only way it would cancel is if I have a positive 2 and a negative 2. Then it would cancel out, wouldn't it, when I add them together? That's why I multiplied the second one by 2, because then it makes there be a negative 2 there. Then that and that will cancel. Yeah.
Are you always going to add the equations once you get to that point?
I always add them, because what I always do is I always make these opposite signs. You can subtract them, but then you have to remember the minus sign kind of carries throughout, so I never do that. I always just add. I just always make sure that these are the opposite sign. Yeah.
So to get x, we could plug it into either?
Yeah, you can plug it into either one. So now that I know what y is, so when I add these together, that goes away. 6 minus 1 is 5. 2 plus 3 is 5. Divide by 5, I get y is 1. Is that cool? And once I get one variable, I just plug it into either one of these. I don't care which one. So if I plug in 1 here, 2x minus 1 equals 3. Add the 1. 2x equals 4. X is 2. So my point 2.
Plug into either one or the original 2?
Yeah, either one of these. Yep.
Over 2.
Because again, the whole idea is it's supposed to be the point where these are the same. That's why it doesn't matter which one you pick. Yeah.
So the substitution and elimination, they should come out to the same answer then?
Oh, hell yeah. They're just, and actually we got 3 different ways to solve the same. I could have used the graphical method. I could have used substitution, but here we use elimination, right? And that's true in all of mathematics. There's a lot of these really difficult problems to solve, and then somebody says, "Oh, if I just draw the picture and move it around, it's easy." So there's a lot of mathematics where you just go, I can't solve it like this. Let me change it and make it and draw it and see what it looks like and move it around and stuff, and then I can do it. So we take the problem and we translate it into a different form. We work it out and then we translate it back. That happens a lot. So here, I could solve this graphically. or I could solve it with substitution, but now we're learning how to do elimination. Yeah.
Like this particular one would have been easy because you already have a y by itself and an x by itself for substitution, but is it mainly to avoid fractions? Is that why you use elimination?
Sort of. But also, I mean, what it leads to is another process to solve. I mean, if we got to next semester, you guys will get to 3 by 3. You'll get to x, y, z. You'll have 3 equations with 3 variables in it, right? And elimination makes that a lot easier. And then there's even a further process using something called matrices. Have you ever heard of that? The Matrix? Not the one where Keanu Reeves? I don't come through. No, but it's a mathematical thing. And it's built off the idea of elimination. So that might be why personally I like elimination, because it's used in a lot of different ways throughout mathematics. But substitution it's used in a lot of different ways throughout mathematics too. So they're both important. So let's solve that a different way. Let's take a step back. How would I solve that substitutionally? So I take maybe like number 1 and solve for y.
Yeah.
So let me just cut to the chase. It would be y equals 2x minus 3. All right, add 1 and subtract 3. Then I could plug that in here. So it'll be negative x plus 3 times this. Where are we at? Okay, cool. Negative x plus 6x minus 9 equals 1. Is that cool? So then you get negative, 5x. Add the 9, you get 10. You get x is 2. And then up here, you know that x is 2. Twice 2 minus 3. Y is 1. Cool. What's up? This is the process we did earlier. So I solve for y first. And don't let that be the stumbling block. You can do it. Subtract the 2x, divide by negative 1, all the signs change. So that's where you get. Plug that in place of y in the other equation, and then solve. Right? We get the exact same answer. The answer doesn't care about the process. There's an answer to this. And there's a lot of different ways to get to the answer. Right? Not all of math is like that. A lot of people think math is very black and white, and one reason it isn't is because there's so many ways to get to that answer, and alternately, in further mathematics, there's not just one answer. It's fuzzy. We're not going to do that. Don't worry. No. So what about, here's an example of one that you would not want to use substitution on. Again, you certainly could. You could always use substitution. Bless you. If I don't say you have to use a certain method, but do you see why you might not want to? You try to solve for any variable, you're going to introduce 2 other fractions, right? And then you have to plug that back into the other. Oh, I really don't feel like doing that. So instead of that, I can start to think about how do I make 2 of these match up so that they'll cancel. So what really sucks is that nothing will cancel right now if I add them together. But also, do you notice if there is a 1, it makes it so much easier. If this was just a 1, I could multiply that first one by negative 5, and then those would cancel. You with me? But here's a cool thing. We know a process already that kind of is related to what I want to have happen here. I want to multiply these 2 so that they meet somewhere. And that sounds like LCD. So what's the LCD of 3 and 5? 15. So what I'm trying to do right now, I know my goal is to get one to be like 12x and the other one to be like negative 12x or whatever, so that they'll cancel.
So you do the bulk of them?
Yes, I love it.
3 and 1 by
So if you multiply this one by 5,
and that's legal because 10x minus 35y.
It's totally legal. Any equation you have laying around, you can pick it up and multiply it by whatever the hell you want to. I don't care. So I have two equations up here laying around. I can multiply the first one by 218 if I wanted to. I don't want to.
Across the whole thing, right?
It's definitely, right? If you only do part of it, it's not a true equation anymore. To keep it true, you got to multiply it the whole way through. So if I multiply by 5, the first one, what do I get? 15x.
35y.
Good. Minus 35y
Negative 55.
equals negative 55. Is that cool? Let me just stop right there. Let me see if you guys get this. What do I want to multiply the second equation by? Negative 3.
You could do like -5 and positive 3.
Sure, of course. As long as they're different signs. What's the only way they're going to cancel? Opposite sides. So I want to make them both 15. That's the LCD. But I want them to be opposite sides. So I got to multiply the second one by negative 3. So this becomes negative 15x
Plus 9y.
plus 9y equals 311. Now if you want to, now I should be doing this, you certainly could put a little negative 3 next to each one so you don't forget. Trying to keep it in your brain about what the hell's going on is not the easiest thing in the world. But now I can see negative 3 times 5 is negative 15. Negative 3 is 9. Negative 3, negative 1 is 3. So you can write what you're doing next to each piece. So we are completely allowed to multiply any equation, both sides, by anything. I know I keep saying it, but except 0. So I'm going to multiply by the things that allow me to have one of the variables cancel. So now when I add these two equations, they are the same equations as these. They've just been built up. It's sort of like saying 6/8 is the same as 3/4. I've kind of like built them up. Same equations. But now when I add them together, those go away. What do I get here? Negative 26y equals negative 52. And thank God 26 goes into 52. That means Jeff thought about this correctly in his head. Minus 2.
Plug it in on the y.
Plug in whichever.
Let me make sure everybody's with me.
You're adding, okay, wait. 1. So
You get a choice at the top. Y is going to be the same.
What's up?
So you did an elimination on both equations so that you could...
Elimination requires me to have both coefficients the same, right? Like over here, we multiply this by 2 so that they end up being... Oh, I did this a separate one. We multiply by 2 so that'd be negative 2x and 2x, right? I only had to multiply one of them because I can make this become a 2. It's a 1 right now, I can make it a 2 easy. Can I make a 3 become a 5 easy? No. Can I make a 7 become a 3 or the other way? No, I can't. So I got to make them both go meet somewhere. And again, I am completely allowed to do this because they're both equations. I can multiply both of them by something. I don't care what. So if I multiply that one by 5 and that one by negative 3, these will be the same number, different signs. Yeah.
So when you multiply each one, does that inflate the number on the
No, because it's balanced with the other side. I think I see where you're going, but no, it doesn't. It's the same exact line. This is a line, this is the same exact line. Because it would reduce back down, wouldn't it? Yeah. What do I do now? I'm not done yet, right? Plug it back in to either one. So I'm just going to plug it into 1. I don't know, just because it's the first thing.
So it's the original equation.
Yeah, in this case, it's one of these two. I definitely wouldn't plug it into one of these. I could, but I wouldn't plug it into one of these because they got bigger numbers to worry about. So in this case, I'm definitely going back up to the original. So 3x minus 14 equals negative 11. Add 14. 3x equals 3. X is 1. So you can see Jeff didn't want to strain his brain too much. I made the point 1, 2. Yeah. So I mean, just think about it. Let's see. If I said solve this system, I said solve that system, what would you do?
Just add it.
Just cross off.
Just add them out, right?
Yeah.
Because these are different. Okay, what if instead of this equation I gave you x minus 2y equals 1? When you just multiply by 4 and make it this equation. So, I mean, when I give you two equations, if there's no variables that have coefficients that match, you're like, well, some jackass reduced again. Let me bring it back up, right? If I gave you that, that's easy. Why is that easy? These go away already. On their own, they're ready to die, right? If I gave you that equation, it doesn't match up yet. I got to multiply it by 4 so that that coefficient will die now. So when I give you this equation, you're saying these don't match up. And the whole idea of matching up, that does sound like LCD. I want them to match. The first place these match is 15. So if I multiply by what he needs to make him 15,
Thank you.
and think about this, with LCD, isn't it just the bottom that tells you what the LCD is? But when you multiply the bottom, don't you also have to multiply the top?
Yes.
Or else it's a different fraction. So I can't just multiply this one piece. I've got to multiply everything to make it the same equation. All right, so there's more of an analogy there than I realized. That's cool. And then once I get these two the same, I add them together. That's my whole motivation for getting them the same. So that when I add them together, that part goes away. And of course, why do I want that part to go away? Because it's freaking two variables. Right? If I can make it one variable, I can get the answer. It's almost like acting class. So much motivation needed to be explained. Okay. So let me give you one more to try on your own here. I'm not going to say anything. And neither are you. Yeah. Oh, what did I just do? I think it was 18, sir. Yeah, what I was doing was. Yep, make that second one 18. x. Let me try to catch up to you guys. Which variable? Not a bad idea.
12.
So it's not a bad idea. In general, I always go for the ones that are already different signs. But damn it, if Jeff didn't give us, neither one of them have different. They're all positive. So then I just pick the ones that are smaller, maybe, right? So between the x's, what's the LCD going to be? 12. So what are you going to multiply the first one by?
3.
Good. You can multiply by 3 or negative 3, as long as one of them you multiply by negative. So if I multiply the first one by a positive 3, so 3 times this, 3 times that, 3 times that, 12x plus 15y, 33, good.
And then negative 4.
And then multiply, I've got to multiply the second one by negative 4.
Negative 12.
Negative 12x, put with negative 4.
28y.
Negative.
Minus 28y
Negative
equals, yeah, negative 72.
You get negative 13y.
Hold on, John. So, I mean, that step by itself, I know I'm allowed to do this. So very often we have all these things we're allowed to do, but we don't know why we'd ever do them until later. We get to a point where we're like, oh, I want to do that, and I'm allowed to do that. So here, I want one of these variables to cancel. So we're allowed to multiply until they would. And now when I add these together, which we talked earlier about why we're allowed to do that, here the x's cancel.
Negative 13y.
Yeah, negative 13y.
It's negative 39.
Okay, equals negative 39. And again, thank God 13 goes into 39. Y equals 3. Bless you. And then to get x, plug it into either one of these. And if you have time, you can plug it into both, because that's a little check. You just hope to God your plugging in isn't where you make a mistake. No matter which one you plug in, your x should be the same. So if I pick the first one, 4x plus 5 times y should be 11. So 4x plus 15 equals 11. Subtract 15. 4x, good Lord, Jeff, equals negative 4. X is negative 1. So the answer is negative 3. That's, again, the point where these would meet if I graphed them. Would you want to graph these? Can you imagine the y-intercept on this one would be 11/5? Nope. Okay. Would you want to do substitution on these? Probably not. I agree with you. Right? Elimination, though, eats them up. That was not typical. Elimination doesn't care about any of the fraction problems that I have with the other two methods. Okay. So, real quick, let me get this out of the way for right now. Looking at these problems, do you see how these problems describe this real-life situation? For, well, this isn't really going to work. That's too bad. It's a negative here. Shoot. But this could be the way. Just forgetting it. 4 hot dogs and 5 hamburgers cost $11. 3 hot dogs and 7 hamburgers cost $18. Do you see how that flows? Wouldn't that be what it is? Because what would X and Y represent? The cost of each, right? 4 hot dogs. Well, if hot dogs are $2 each, that'd be $8 there, would it? So that's my feeble attempt to segue into word problems. And I think I'm going to use the blue book for this because they have some good examples in there. Oh, before I forget to...
So that's 3.4 to 3.7.
What's that?
That'll be 3.4 to 3.7. Because the test
Yeah,
numbers
yeah.
are
3.3. Yeah.
Okay, so 3.3 to 3.7.
Yeah. But I mean, the idea is that 3.1 and 3.2 cover. They're in the other ones too, so you can't really escape those. at page 53. I want to point out two things. The next page after 53 is a mistake that they did. This is actually from section 10.3. I have no idea why they decided to stick that here. So if you're looking through this, don't freak out. And something else I wanted to show you is they have like a chapter 4 review with a bunch of problems from chapter 4, and thank God they even have the answers. So this is not this book is a really decent study guide for that. Okay, so it's always kind of funny to me to read some of the word problems that people come up with for algebra. And sometimes the word problems are the reason that students kind of like, well, algebra's a bunch of shit. How would the farmer, I love this, how would the farmer know that there's 62 legs out there, but he doesn't know how many ducks and cows there are? But we'll go with it. It's kind of a classic, has anybody ever heard of a problem like this? It's a classic problem where they say, there's so many cows and there's so many ducks and this many legs. The thing about the legs, what is it about the legs in this case?
One has 4 legs.
Yeah, the cows have 4 legs and the ducks have 2. What are my variables? What are my unknowns? The number of ducks. Remember, that's always where we start. Is what is it that we're talking about? Yes, it says ducks. And what? Now here's the difference. When I'm using systems of equations, the whole point of it is I have 2 variables. So I can call ducks. What's a good thing to call it ducks? D. No way. D. And then the cows we'll call C. I like it. I was waiting for it. I should have known. Where's my fellow smart asses?
Did you want to fix this for the?
Second.
I don't know if you wanted to like zoom that into that or not.
Duty.
The camera.
Oh,
It was over there, so I wasn't sure if you needed to like. I
Thanks.
tried to turn it, but I didn't want to break it.
Sometimes I forget I even have this thing going. For those who left early today for whatever reason. Okay, cool. Thank you. So there are 2 unknowns. There must be 2 equations I can make. If there were 3 variables, there are 3 unknowns, there would have to be 3 equations I can make. However many things I don't know, I must also have that much information to be able to figure them out. Does that make sense? That's why up till now we only had 1 equation with 1 x in it. That's all we needed was 1 equation to figure it out. So what are my 2 equations here? He's got 24 animals. So what would the equation be that leads up to 24? Yeah, the ducks plus the cows is 24. Now I cannot also say d plus c equals 62. That just doesn't make any sense. That would lead to no solution. They can't add up to be different numbers. How do I make the 62 legs? What were we saying earlier? Every duck has 2 legs. So 2 legs per duck plus 4 legs per cow gives me 62 legs. So the idea here is 24 is number of animals. So on the other side, I better have number of animals plus number of animals. And D and C represents number of ducks, number of cows. 62 is legs. So on the other side, I better have legs plus legs equals legs. 2D is duck legs. 4C is total cow legs, right? Do you understand? So that's how you make sure. You make sure each piece, actually, if I have money, I better have money plus money equals money. Right? Doesn't make any sense to add Fred plus Bob to make 100. What do you want? You're going to sell poor Fred and Bob for just $100. It's no. You got to be worth more than that, right? Okay, and now you can use whatever the hell way you want to go. You can elimination. You can use substitute. We got our equation set up. So which way do you guys want to do it?
Elimination.
All right, I like it. If I use elimination. What can I do to this guy? Now, real quick, you guys notice that I could divide this one by 2? But I mean, it's actually a little quicker just to go ahead and multiply this other one by -2. What do I get when I multiply this by -2?
Negative 2D.
Negative 2D
minus 2C
Good, minus 2c
equals negative 48.
equals negative 48. I love it. So we did that. We multiplied this one by negative 2 just so these would cancel when I add them together. So now when I add them together, these cancel. 4c minus 2c. 2c equals 14. Right, just 62 minus 48. So then how many cows are there? 7 cows. Right. Waiting to be swept up by the next one. So if C is 7, how do I get D? Yeah, I'm going to plug it in the easy one here. D plus cow 7. Subtract the 7. There must be 17 ducks. Now this one, you don't have to make it a point. Really. I mean, you can leave it like that. It doesn't have to be a point. I'm not necessarily going to graph my duck and cow lines. It doesn't make sense. This is a physical problem. I can pretty much stop when I get the parts identified. Is that cool? Mathematically, I could write it as a point. That's where those two equations would meet. But my ducks and cows don't care about that. So any questions on that first problem? It's a very classic problem. One equation is the total. And the second equation is something to do with each piece. So very often you'll see a problem like I got $1,000 and I want to put it, some of it in a 5% account and some of it in a 9% account to make so much money. So my first equation would be a total equation. A plus B equals $1,000. And my next equation would be an interest equation. 5% of this plus 9% of that equals how much interest I want to make and so forth. Then I would figure that out. So very often I have one equation very simply, variable plus variable equals the number they gave me. But what about number 2 here? Very first thing you look for before you do any mathematics is just what's the players involved. So what's involved here? Okay, we got airplane. Good. We got coach, number of coach seats, and number of first class seats.
So the first one would be what? F plus C equals...
All right, good. So we're going to call this C, call this F. That makes sense to me. So again, like I said, you almost always have where you just add the two things together. The coach seats plus the first class seats has to be 152. Right? Nobody is sitting outside the plane. Now the second one is very direct. The number of coach class seats is, so just help me out in mathematics. The number of coach class seats is, how do I translate that? Careful. The number of coach class seats is, translate that. C equals 5 more than 6 times first class.
6x plus 5.
Yeah, either 5 plus 6f or 6f plus 5. I like it. Plus is the one thing where you can add, it doesn't matter what order you add it.
You just plug in.
Now what method seems to be, is everybody cool with setting that up? Do you understand, even if you have a little trouble with this, can you see how these word problems are so much easier to set up than the ones we did earlier? Do you remember those? I always think that ones we did earlier are a little more vague. You kind of have to piece it together. This is kind of like it just goes right into it. Hopefully you guys see that. What's it kind of set up for already? Yeah, so what method is it set up for? Substitution. So I could take, if I wanted to do elimination, I could certainly subtract the 6f over and do elimination. But this is already set up for substitution. If I take the first one and I rewrite it C, but C is 5 plus 6f. That's C. Plus F is 152. So C plus F is 152. C plus F is 152. So I just rewrote the first equation, replacing C with what it is. And now I can solve that equation. Five plus 7F equals 152. Then, of course, you subtract 5. Take it up here. 7F equals 147. Yeah, thank God 7 goes into 147. So I got 21 first class. How many coach do I have? Yeah, just plug it back in here, right? C equals 5 plus 6 times 21. 5 plus 126. 131. And does that do what it's supposed to do? 131 seats plus 21 seats is 152 seats, thank God. Yeah.
You want in that answer or like the sentence?
Oh, I'll tell you what, as long as you set something like this up, you tell me what these represent, I'm cool with you not even, just writing it like that. Because C is 131, and 131 is the number of coach seats. Yeah. So you could put down here, coach seats or not, I don't care. As long as you set this up, you covered yourself. Now, I'm pretty sure I didn't assign one like number 3 in the homework. I'm just going to skip that for now. I want to go do one like from here. And we'll probably call it a day after this. Try number 12. This is on page 60. I like that. You are not adults because you are students. Kind of easy. What's up? Yeah. The only things we don't know are coach and first class. No. Because this is a physical problem. All we need are the two things. There's no, mathematically, these are lines that would meet at that point. Physically, all I need to know is the number of coach and the number of first class.
Okay.
There's no need to put it at the point.
On this one, you just stop it there, so you just plug in C, just C plus.
Yep,
seven.
yep, exactly. And they solve for D. Cool. Lock it. Alright, so what are my two unknowns? The number of adults, the number of little students. So equivalent enough, I would call that A and S. The S might be a bad idea for me.
5.
Yeah, so let's call it A and T for me. You call it A and S if your S's look like real S's. That's nice. So the first equation I can write, and it might sound like there's not enough information, but they give me two pieces of information. They tell me how much total money. So I'm going to have a money equation, and then tickets. I'm going to have a total equation. So almost always that first equation is just, add the variables to get a total number. So adults plus students would be 35. Now how do I convert those into money? Yeah, every adult gave me $3. Yeah, 3 for every adult, plus 2 for every student, right? So this much money I got from the adults plus this much money I got from the students has to equal what? The total money I got. Cool. This is what I meant. Number of people, number of people, number of people. Money, money, money. And now, what method seems to be better here? Yeah, elimination. Multiply by what? Negative 2 or 3. I'm going to multiply by negative 2. Just because. So I get negative 2a minus 2t is negative 70. Is that cool? Just multiply this whole thing by negative 2. That's what it becomes. And the reason I did that is so that my t's cancel. So 3a minus 2a.
Okay.
A. 80 minus 70. 10. So if a is 10, t has to be 35 minus that. T has to be 25. Is that cool? And then to check it, I could do 3 times 10 is 30, plus twice 25 is 50, 30 plus 50 is 80. Yes, it works. Yeah.
I know where I went wrong because I did a plus t equals 80.
Ah.
I mean, but how do you know which one to? How did you know not to use 35 instead of 80?
Because the money is an extra step. In order to figure out how much money I made from the adults, I have to first know how many adults were there. Right? So I know I want to set my variable up to be the most basic thing, which is the number of each kind. Because then I can build it to be money. Well, if there are A adults, I made 3A money off of them, 3A bucks off of them. Do you see what I'm saying? So your variables will almost always be the number of this, the number of that.
Okay.
And then you multiply it to be something else for the next equation. How's that? Is that all right? So again, you don't have to write that as a point. 10 adults, 25 students. The students outnumber the adults. Oh no. So that's section 4.4, yeah. All right, and that's the last section we do in chapter 4. So next time we're going to get into polynomials. And then eventually like FOIL method and all that stuff, if you've ever heard of that. Oh yeah? Cool. All right. See you guys tomorrow.